Welcome you all. In today's lecture, we are going to study what is meant by Compton effect. And in this lecture, we have to include what is meant by Compton effect, then what is meant by Compton shift, experimental arrangement of Compton effect, failure of classical physics to explain Compton effect, then quantum mechanical explanation of a Compton effect. So let me start with what is meant by Compton effect. This Compton effect was first discovered by a scientist A.H. Compton, and it was discovered in the year 1921. So this effect was actually related with an interaction of light with a matter, and this interaction of light with matter was first discovered by the scientist Thomson. But Thomson has studied the interaction of light with a heavy elements. Heavy elements means whose atomic mass is higher, and that's why Thomson observed that when light interacts with a matter, or there is a scattering of light from the heavy element, then the wavelength or frequency of the scattered light and wavelength or frequency of the incident light, they are same. There is no change in the wavelength or frequency of scattered light. And later on, Compton repeated same experiment but with a light element. Instead of using heavy element, he used light element like a graphite. And what Compton has observed, when a light, and he used X-rays, so high frequency light, that is X-rays. So when X-rays interact with a light element like graphite, then these X-rays will get scattered, and scattered X-rays shows two intensity peaks. There exist two intensity peaks, and here it is observed that one peak corresponds to the original wavelength, while other peak corresponds to the slightly longer wavelength. That original wavelength, peak corresponding to original wavelength, is called as the unmodified wavelength, while the slightly longer wavelength or peak corresponding to slightly longer wavelength is called as the modified wavelength. So what Compton has observed, whenever X-rays are allowed to scatter from the light element like graphite, then scattered radiation shows two peaks. One corresponds to original wavelength, that is called as the unmodified wavelength, and other corresponds to the slightly longer wavelength, and that is called as the modified wavelength. And therefore we can define Compton effect as the phenomenon of splitting of incident wavelength of X-ray into two components from graphite. So the phenomena of splitting of incident wavelength of X-ray into two components from graphite is known as the Compton effect, which was discovered by scientist A.H. Compton in the year 1921. Now, what is meant by Compton shift? So Compton shift is nothing but it is a difference in two wavelengths, that is difference between a longer wavelength and the original wavelength. That difference between two wavelengths is called as the Compton shift, and it is denoted by delta lambda. So here Compton shift delta lambda is equal to lambda dash minus lambda, where lambda dash is the longer wavelength, that is modified wavelength, while lambda is the original wavelength, that is unmodified wavelength, and lambda dash minus lambda, that is difference between original wavelength and modified wavelength. That difference is called as the Compton shift, which is denoted by delta lambda. And Compton observed that this Compton shift does not depend on the wavelength of the incident X-rays, as well as it does not depend on the nature of the scattering material. It only depends on the scattering angle, that is phi. So Compton shift delta lambda is directly proportional to the scattering angle phi, while it is independent of the nature of the scattering material as well as the wavelength of the incident light. So this is Compton effect. Now we have to study the experimental arrangement of a Compton effect. So experimental arrangement of Compton effect is as shown in figure. Here you can see this is a X-ray. So X-rays are obtained from the source of X-ray, that is the X-ray tube. So X-rays obtained from the X-ray tube of a known wavelength are allowed to pass through the slit S1. So all slits S1, S2 and S3, these are used to focus the beam so that a well-defined beam of X-rays can be obtained, and for that purpose slits are used. So when X-rays of known wavelength are allowed to pass through the slit S1, then well-defined beam of X-rays will be obtained. Then that beam of X-ray is allowed to incident on a scatterer. Scatterer means light element like a graphite. So graphite is used as a scatterer, and here this incident X-ray beam, when strikes with the graphite, then that beam will get scattered, and that scattered beam is allowed to pass through the slit S2. After passing through the slit S2, that scattered beam will incident on a crystal analyzer. So crystal analyzer is set at a proper angle, and as soon as this scattered beam incident on a crystal analyzer, then from the crystal analyzer that beam will get reflected. Again that reflected beam is allowed to pass through the slit S3. That beam passes through the slit S3, and finally that reflected beam enters in a ionization chamber. So as soon as reflected beam enters in the ionization chamber, that beam of X-ray will ionize the gas and it will produce a ionization current. The ionization current produced is directly proportional to the intensity of the X-rays. So indirectly, in terms of ionization current, we can measure the intensity of X-rays. So when that reflected beam enters in an ionization chamber, it ionizes the gas and produces ionization current, and that ionization current can be measured with the help of a microammeter. Now for different wavelengths, we can use the X-rays of different wavelength, and for different wavelength we can measure the intensity of X-rays by rotating this ionization chamber. We can rotate this ionization chamber along the circular wavelength scale. So circular scale is attached to the ionization chamber, and that's why if we change the position of the ionization chamber, then corresponding wavelength can be detected. So for that purpose this circular scale arrangement is provided. So this is an experimental setup of a Compton effect. So experimental setup which contains X-rays from the X-ray tube incident on graphite. Here it will get scattered. Scattered rays incident on crystal analyzer. Here beam will be reflected. Reflected beam enters in the ionization chamber which is filled with a gas. So it produces ionization current. Ionization current is measured with the help of a microammeter, and ionization chamber gives the intensity of the X-rays. And for different wavelengths, we can to detect different wavelengths, we can change or adjust the position of ionization chamber along a circular scale. And in this way, same procedure again can be repeated for different values of scattering angle phi. So same procedure can be repeated for different values of scattering angle, that is phi. And the experimental results which were observed by Compton are as shown in this graph. So to study the experimental result, we have to plot the graph between wavelength and the reflected intensity, that is intensity of X-rays, which is measured in terms of ionization current. And experiment was repeated for different scattering angle. So we have drawn 4 graphs. For phi is equal to 0, this first one, then for phi is equal to 45, phi is equal to 90 and phi is equal to 135. So from experimental results, it is observed that when we plot the graph between wavelength and resultant intensity or reflected intensity, then when scattering angle phi is equal to 0, we get only one peak. Only one peak means there is no modification in a wavelength. No modification in a wavelength means Compton shift is equal to 0, and as Compton shift delta lambda, which is equal to lambda dash minus lambda, is equal to 0, it means lambda dash is equal to lambda. So here lambda is equal to lambda dash, and that's why we get only one intensity peak. So no Compton effect was observed here. Now if we increase the scattering angle phi, suppose phi is equal to 45 degree, then we get 2 intensity peaks. One peak corresponds to wavelength lambda, that is the original wavelength, and other corresponds to lambda dash, which is a longer wavelength, and that is the modified wavelength. So modified wavelength denoted by lambda dash, original wavelength denoted by lambda, and difference between these two wavelengths will be delta lambda, that is the Compton shift for phi is equal to 45 degree. Again increase the scattering angle phi. Now for 90 degree, the graph between wavelength and reflected intensity is as shown in figure. Again we get 2 intensity peak. One corresponds to original wavelength lambda. Second peak corresponds to longer wavelength lambda dash. And difference between two is the delta lambda. So you can see initially when phi is equal to 0, Compton shift is 0. As phi increases, we get Compton shift delta lambda. Again phi increases, then Compton shift delta lambda also increases. So difference between two wavelengths goes on increasing. And for 135, again we get 2 intensity peaks. One for original wavelength lambda, other for longer wavelength lambda dash, and difference between two delta lambda is more. So from these experimental results, it is observed that the scattering angle phi, so from this result it is observed that Compton shift delta lambda is directly proportional to scattering angle, that is phi. And it is observed that Compton shift is independent of the wavelength of the incident X-rays. There is no effect of wavelength of an incident X-ray on a Compton shift. If we change the wavelength, then Compton shift does not changes. So it is independent of the wavelength of incident X-ray, as well as it is independent of the nature of the scattering material. Even though the scattering material is changed, still the Compton shift does not changes, means Compton shift is independent of the nature of the scattering material. It depends only on the scattering angle phi. So delta lambda Compton shift is directly proportional to phi. Now we have to study failure of classical physics to explain the Compton effect. Means how classical physics fails to explain the Compton effect. Actually, Thomson have already studied the same interaction, that is interaction of light with a matter, and he applied classical laws. And according to classical laws, there should not be the change in a wavelength. There should not be any modification in a wavelength. So according to classical mechanics, light is nothing but it is an electromagnetic wave. Means it is a variation of electric field vector as well as the magnetic field vector. Out of these two, electric field vector is the light vector. Means electric field vector represents the light energy. So whenever that light or X-rays strikes with the scattering material, then electric vector of that incident light will interact with the loosely bound electrons of the atoms of a scatter. What may be the atoms present in a scattering material? It contains loosely bound electrons, and that light or X-rays interact with that loosely bound electron. When that light interact with that loosely bound electron, what may be the frequency of the incident light? With that frequency, that electron starts to oscillate. So electron starts to oscillate with the same frequency, and when electron starts to oscillate, then it emits the electromagnetic radiation. So radiation will be emitted by that oscillating electron, and frequency or wavelength of the emitted radiation will be same as that of a frequency or wavelength of the oscillation, which is equal to the frequency or wavelength of the incident light. Means the wavelength or frequency of the scattered radiation or emitted radiation is equal to the wavelength or frequency of the incident radiation. Means there is no change or modification in a wavelength. This is what classical mechanics has suggested. But in Compton effect, it was observed that whenever X-rays are allowed to scatter from the light element, then there is a modification in a incident wavelength. We get original wavelength as well as the slightly longer wavelength. And why there is a modification in a wavelength or frequency of a scattered X-rays, this cannot be explained by the classical physics, and that's why classical physics fails to explain the Compton effect. And finally, we have to study the explanation of Compton effect on the basis of quantum theory or quantum mechanical explanation of a Compton effect. So here, according to quantum theory, X-rays, which is nothing but the light, and it consists of photons. So when X-ray will strike with the scatter, then there is 1:1 interaction, what Einstein has suggested in case of photoelectric effect. Similarly here, what Compton has suggested, explanation of this Compton effect by using quantum theory was given by Compton himself. In photoelectric effect, it was discovered by Hertz, but its theoretical explanation was given by Einstein. But in Compton effect, it was discovered by A.H. Compton, and its explanation, theoretical explanation, was given by Compton himself. So Compton initially assumed that the electrons, that loosely bound electron in a scatterer, is at rest. It was assumed by Compton that the electron is at rest and it is free to move. So this is electron which is at rest. and that's why its kinetic energy will be equal to 0. It is at rest and it is free to move. Now when X-ray strikes with a scatter, X-rays consist of photons. So we consider a photon of X-ray whose energy is h nu. So E is equal to h nu, means nu is the frequency of a X-ray, and therefore its momentum, we have already calculated the momentum of photon when we have studied what is meant by photon and properties of photon in previous lecture. So momentum of photon is h by lambda. So energy of incident photon E is equal to h nu and momentum is h by lambda. This photon strikes with the electron which is free to move, but it is at rest. As soon as that photon strikes with the electron, there is a elastic collision. There is a elastic collision, and because of this collision, what will happen? That electron will get recoiled. Electron will get recoiled means it gains some momentum. Alright, so it acquires some kinetic energy, and that's why energy of the photon is utilized to recoil electron, and recoil angle is denoted by theta. So electron will get recoiled, while that photon, incident photon, will get scattered. It will scatter along this direction, and that's why angle made by scattered photon with the incident direction is called as the scattering angle, and it is denoted by phi. So phi is the scattering angle, this is the scattered photon. So scattered photon has a new energy, and that energy is denoted by E dash is equal to h nu dash. H is the Planck's constant, and P dash, therefore corresponding momentum will become P dash is equal to h upon lambda dash. Means what is the frequency of the incident photon? That is nu, and wavelength is lambda. So energy of the incident photon is transferred to electron, means energy of the scattered photon will be decreased. Its energy decreases means its frequency decreases, because energy is directly proportional to frequency, and it is inversely proportional to wavelength, means wavelength increases, and that's why scattered photon has a slightly longer wavelength. And this is an explanation which was given by Compton, that is why there is a modification in the wavelength of a incident X-rays. So here he suggested that there is a elastic collision. During that collision, some energy is transferred to electron. Electron will get recoiled and photon will get scattered, and that's why scattered photon has a less energy than the incident photon. Less energy means less frequency. Less frequency means longer wavelength. And he derived the formula or expression for the Compton shift, and according to Compton theory, Compton shift, that is delta lambda. Delta lambda is the Compton shift, and according to Compton shift delta lambda is equal to h upon m0c into 1 minus cos phi, where h, whose value is 6.63 into 10 raised to power minus 34 joule second, and it is Planck's constant. Then m0 is the rest mass of electron, which is 9.1 into 10 raised to power minus 31 kilogram. That is rest mass of electron. And c is the speed of light, which is 3 into 10 raised to power 8 meter per second, and that is speed of light. And now using these values we can determine the value of this constant, and from this here it is observed that h upon m0c is equal to 0.0242 angstrom unit. So if we use these values of constants, and we can easily derive the value of h upon m0c, which is 0.0242 angstrom unit. And if we use these values in this equation, so for phi is equal to 0, if you use phi is equal to 0 in this equation, then equation 1 becomes delta lambda is equal to h upon m0c, that is 0.0242 into 1 minus cos phi. Phi is 0, so cos phi is 1, 1 minus 1, that is 0, and that's why it is equal to 0, which was observed in a experiment. Similarly, when phi is equal to 90, for 90 degree, equation 1 becomes delta lambda is equal to 0.0242 into that cos phi becomes equal to 0 for 90 degree, and that's why it will be equal to 1, and hence it is equal to 0.0242 angstrom unit. Then for phi is equal to 180 degree, then equation 1 becomes delta lambda is equal to, that is 0.0242 into, now for phi is equal to 180, cos phi is minus 1, so it becomes plus 1, 1 plus 1, that is 2, and therefore it is 0.0484 angstrom unit. And from this equation it is observed that as phi increases, the value of Compton shift also increases. So Compton shift, that is delta lambda, is directly proportional to scattering angle phi, which was proved by the Compton theory, which was given by Compton himself using Planck's quantum theory. So this is explanation which was given by Compton himself to explain the Compton effect. There might be one question, why there exists a original wavelength? Modified wavelength is known to us because of the scattered photon, that is during elastic collision energy is transferred to electron, and that's why energy of the scattered photon decreases. But why there is the original wavelength? So for that, whenever what will happen, along with the electrons which are present in the outermost orbit, they are loosely bound, but there are certain electrons which are tightly bound with the nucleus, and it is not necessary that all the photons will interact with only loosely bound electron. There is a possibility that some electrons will interact with a tightly bound electron, and when that photon interacts with a inner tightly bound electron, then in this equation we have to replace this mass of the electron by the whole atom, because that electron is tightly bound with the nucleus, and that's why when that photon has to interact with that electron, tightly bound electron, means he has to interact with the atom itself, and that's why we have to replace this mass of the electron by the mass of the atom, and therefore that equation becomes delta lambda is equal to h upon m into c into 1 minus cos phi, where m is the mass of an atom and capital M is much greater than m0, and if capital M is much greater than m0, then delta lambda will become very small, which is equal to 0, and it implies lambda is equal to lambda dash, and that's why we get a original wavelength. So we can say that when incident photon interact with loosely bound electron which is present in outermost orbit, then we get a longer wavelength, because that photon will get scattered. But when that photon interact with inner tightly bound electrons, then in that case it cannot scatter the atom, and that's why energy of the photon will not change and we get the original wavelength. So this is a explanation of Compton effect by using quantum theory. Thank you.